have a point up here, let's just say x, y. Right? If it's symmetrical about the x-axis, that means that you could flip it over the x-axis and you would have the exact same point on the bottom. It's really easy to use the graph to help you remember these rules, because if you flip that same point over and it's now down here in quadrant 4, what would the ordered pair be if the point up here was xy? X negative y. You'll see how that kind of comes into play. And you could draw a little graph there if you wanted. I'm just drawing points. And if you have a point that's symmetrical about the y-axis, same idea here. If I have a point over here, and if I flip it over the y-axis, I would have the identical reflection of that graph on the other side. And to think about what would that point be, you just have to think about the signs, and what would this point become? Yeah, negative xy. So for every point xy, there's a negative xy also on the graph. If a point is symmetrical about the origin, I don't know, some people struggle seeing that one a little bit more, but it's kind of like you flip from this quadrant to this quadrant, or from this quadrant to this quadrant. So if I have a point up here, xy, and I flip it over, both the x and the y are going to change, right? So I'm going to get negative x, negative y. I kind of wrote this out down here at the bottom, and it's up to you if you're going to write down. If that makes sense to you, you might not need to write this down. But the rule is, if a graph is symmetric with the x-axis, then if xy is on the graph, then the point down here, x negative y, is also on the graph. And we're going to do some testing for symmetry with equations, and this is how we're going to do it. So, I don't know, I feel like the graphs kind of make a lot of sense, but if you like to have words out, like steps out, you might want to write that down. So I just have all this. I kind of did lots of quotation marks here, so I got lazy with my typing. But if it's symmetric with the y-axis, if any point xy is on the graph, then the negative xy would also be on the graph. And if something is symmetric with the origin, that means that both the x and the y would change. So if xy is on the graph, so is negative x, negative y. So part of your homework today is going to say test for symmetry with the x-axis, the y-axis, and the origin. And this is how we're going to do it. And that's my first examples here when we're done writing this. Some graphs have no symmetry, like they won't be symmetrical with any of them. Some graphs are symmetrical with all three of them. Think about a circle centered at the origin. It would be symmetrical with the x-axis, the y-axis, and the origin. So there's more than one answer sometimes, and sometimes the answer is no. So keep that. Notice it says use algebraic tests to find symmetry, which means they're not wanting you to graph this. They want you to use those rules there. And the biggest part is remembering it. I always feel like on a quiz or a test, you don't need to memorize all those. Just think about it. If it's the x-axis, I'm flipping it over, what's changing? It's really easy to remember that way. But I'm just going to go through here. X-axis. I'm going to test each one. And you'll see very quickly that you want to test all three. But you're going to see very quickly, it's going to be easy to see, is it going to stay the same or is it going to change? That's what I'm looking for. So what I'm looking for is when I plug in negative, no, what was the x-axis one? X negative y, wasn't it? X negative y, do I get back the same thing as when it was just x and y? So what you're going to do for test for symmetry is you're going to plug in that ordered pair that changes and see if you get back the exact same thing. So if I go up here and I will leave x as x, but I replace y with negative y, do I get back an equivalent equation? Does that equal the exact same thing that I started with? the x is the same, but the y changed. This is no longer the same equation, so that's a really easy way to say this is not symmetrical with the x-axis. You want to get back to the same thing, because if it's symmetrical, when you plug in that different ordered pair that I gave you, you should get back to the exact same thing that you started with, because that means you get the exact same graph. So you'll start to be able to do this without actually a whole lot of work. The y-axis, think about the y-axis, we flip it over the y-axis, so the x is what changes signs, the y stays the same. And a lot of times you can just tell by looking, I'm going to show work since it's our only example that we're doing with this, but a lot of times you can think about, okay, if I plug in a negative x, is it going to stay the same, or is it going to change? Y isn't going to change because I'm not changing y. And do I get back the same thing? Negative x squared, isn't that just x squared? Yes? And because that equals exactly what I started with, that means that this is symmetrical with the y-axis. You see how you don't really have to show a whole lot of work on this? Because if it's a even exponent, and you plug in a negative x or a negative y, will you get back the same thing every time? Yes? Anyone have any clue what I'm saying? Okay, we'll just show origin. We got to change both of them. If you plug in a negative x and a negative y, are you going to get back the same equation? I already did it over here, that when I plugged in a negative y, it changed that. Like, definitely by the time you get to the origin, you shouldn't have to show a lot of work there. But I can plug it in, negative x squared minus negative y. I'm going to get x squared plus y equals 0, which is not true. So which of these is it symmetric with? Well, in this case, my y-axis is my only one that it's symmetrical with. If I graph this, it would be symmetrical with the y-axis. It could be none, it could be more than one, so just keep that in mind. Even and odd functions. Last year we talked about even and odd functions a lot with graphs. Remember an even function, the arrows go in the same direction. Odd function, arrows go in opposite directions. We're going to start looking at even and odd functions without looking at the graph. And so a really easy even function to think about is the function y equals x squared. Hopefully you kind of know what the equation y equals x squared looks like. What shape is y equals x squared? Hello, is anyone out there today? What shape is y equals x squared? A parabola. I could even say it's a parabola that starts at 0, 0 and looks like this. That is an even function. One way to know that you have an even function is it's symmetric with the y-axis, which means it's really easy to check if it's even. When you plug in a negative x, do you get back the same thing? Just like we just did with the little test for symmetry. You can test to see if something is even by checking to see if I plug in a negative x value, does it not change the problem? And that's what I was just talking about before. With even exponents, if I have an even exponent and I plug in a negative number, do I always get back the same thing as if I plugged in a positive number? That's what makes a parabola so great. For every positive number you pick, you're going to get the same y value when you plug in a negative number, because negative 2 squared is the same as positive 2 squared. Yes? Yes. Whew. You guys are killing me today. Blank stares, not a good thing. Chapter 1, not good. the exact opposite of an even function. An odd function means that for every x value that you plug in that's negative, you get back the negative y value also. So odd functions are functions that are symmetric with the origin. And think about what we just talked about. Symmetry with the origin means it kind of flips over from one quadrant to the diagonal quadrant. Really easy odd function to remember is y equals x cubed. It's kind of like an S-shaped function. It still goes through 0, 0, but it kind of goes up like this, and this side goes down like this. That means if you plug in a negative x value, for all negative x values you plug in, you're going to get a negative y value to go with it. So another part of your homework today is going to be looking at functions, not graphing them, and saying, is it even or is it odd? And there's a good chance it's not going to be either one, because there's a lot of graphs that are not symmetric with the y-axis and are not symmetric with the origin, and the answer is they're going to be neither even nor odd. So let's practice. So even in odd functions, we could actually just do the two tests. We could test for symmetry with the y-axis. We could test for symmetry with the origin. But the easiest way is to just plug in negative x, and you're looking for a couple things. If it's even, when you plug in negative x, nothing should change. You should get back the exact same problem that you started with. If it's odd, you should get back the exact opposite problem. Like you should be able to factor a negative out and then have the same problem there. If it's somewhere in between, like some things change signs and some things don't change signs, then it's neither. All right, so you're looking for either the exact same thing, the exact opposite. If you just look back at what we wrote, if it's even, when you plug in a negative x, nothing changes. You get back the exact same thing. But if it's odd, when you plug in a negative x, you get back the exact opposite function, which means you could factor a negative out and then have the same function with a negative in front. So if I do that for this problem, all I'm going to do is plug in a negative x. And I'm going to get negative x times the square root of 1 minus negative x squared. Do you agree that this negative x squared is really just going to stay as 1 minus x squared? So now here's the question. Is it even? Did it stay the same? Because isn't negative x squared just x squared? But don't we do exponents before we multiply? That's just order of operations here. 1 minus negative x squared would be like 1 minus negative x times negative x. Right, Logan? Order of operations. I need to multiply, or I need to do my exponents before I cross out two negatives. And negative x times negative x is just positive x squared, so then I would still have that 1 minus in front of it. Like, you can't just automatically cross out two negatives if there's an exponent next to it. Exponents first. Other questions about that problem being simplified? So is this even? Did I get back the exact same problem that I started with? Definitely not. I have a negative out here, so it's not even. What about odd? Is it the exact opposite of what I started with? confused by this one. I would say yes also, because this is multiplication, and if I factored out a negative from this, I only take that negative out one time. Like, I don't distribute that negative, and people get really confused by multiplication as opposed to addition. Right? If you have negative x plus 3, you have to distribute that negative to both things. This is not addition, this is multiplication. If you have negative 3 times x, you don't give that negative to both the 3 and the x, you would just write negative 3x. Right? There's a big difference there between taking a negative out of addition and taking a negative out of multiplication. This is exactly the opposite of what we started with, which means this is an odd function. Which means if you graphed it, it would be symmetric with the origin. Even and odd are going to come into play a lot more later when we deal with trig functions and graphing trig functions. Okay, that one was kind of a hard one. We started with the hardest one. It'll get easier from here. So try this one before I just do it for you. Plug in negative x and see if you get back the same thing, the exact opposite thing, or somewhere in between. Plugging in negative x squared is just going to be x squared. 2 times negative x is going to be minus 2x minus 3. Is that even? No, it did not stay the same. Is it odd? Is it the exact opposite of what I started with? Which means it's somewhere in between, because this one didn't change, but this one did change, which means I can't be even or odd, so we would say neither on this one. You might not even need to do the work on this one, because you might even think about, if I plug in a negative x on number 4, what's going to happen when I plug in a negative x to x to the 4th? And what's going to happen when I plug a negative x into x squared? It's going to stay the same, right? I'm going to get back the exact same thing, because an even exponent will always give me back the same thing, no matter if I plug in a negative or a positive. So sometimes you don't even need to do the work here. If you plug in a negative here, you're going to get back x to the 4th. Plus x squared plus 2. It's exactly what I started with, which means that's an even function. Totally running out of time. All right, horizontal asymptotes. Try not to get overwhelmed by this. This is how we write a rational function. You don't have to write all this down. Here's what I want you to notice from this. The numerator, this is like, remember we talked about leading coefficients? This is the highest degree, and it just counts down. You don't really have to write that. You could just write a to the n, x to the n, and then just write dot, dot, dot. And on the bottom, this would be your leading coefficient with the degree of the bottom plus dot, dot, dot. But you should notice every time we write a rational function, the degree goes down by 1, and then the leading coefficients, they just write those next to them. That's just algebraically how they write the formula for a rational function. We talked about vertical asymptotes a little bit yesterday. You graphed some problems yesterday that had vertical asymptotes. We didn't talk a lot about horizontal asymptotes, and that's what I really want to get through this slide before the bell rings. So again, you can summarize that. You don't have to write all that down, but it's going to come into play here. Nick asked earlier on that one, how did I know that that was a vertical asymptote? How did I know to make a dotted line? Vertical asymptotes are always at the zeros of the denominator. So that means set the denominator equal to 0 and solve it, and you will always have your vertical asymptotes. That's also what your domain is, like the opposite of the vertical asymptotes. We also had horizontal asymptotes, and there's rules for these, and that's why I wrote this out. You might think, why would she show me such a terrible thing? Because horizontal asymptotes have to do with the degree of the numerator and the degree of the denominator. There are 3 options, and even if the bell rings, I want you to stay right here. Horizontal asymptotes. This is the numerator degree, this is the denominator degree. If the numerator is less than the denominator, then you will always have y equals 0 as a horizontal asymptote. That's the x-axis. You have that a lot. If the numerator is less than the denominator degree. If the numerator is equal to the denominator, here it is. I don't know why this moves around every time. If the numerator is equal to the denominator, again, why did I write this out up here? These are your leading coefficients. You take the leading coefficients over each other, and that's your horizontal asymptote. It means it could be any number, whatever the leading coefficients happen to be. And the last one's the best one. If the numerator is bigger than the denominator degree, there will be no horizontal asymptote.
Castro and Ronald back to the office, please.
Your homework is day 2 on your assignment sheet, and I'll go to it in just a second if you don't have your assignment sheet. There's some graphing ones on there. Attempt them. Tomorrow we'll do a few examples of graphing, all right? But you should be able to do most of it. Use your book, right? All this stuff is in your book.